So this experiment, we're going to look at the properties of acids and bases. Now, one of the definitions for acids and bases are as follows. Acids produce H plus or H3O plus. These are equivalent. This is just a shorthand way of writing H3O plus. Bases produce OH minus. And both of these are in aqueous solution. So if I was to write a chemical equation, I might say I take HCl and I react it with H2O. And this produces, this hydrogen is going to actually jump over to this guy to make H3O plus plus Cl minus. Now if you'll notice, aqueous, aqueous. I have 3 hydrogens on the reactant side. I have 3 hydrogens on the product side. I have 1 oxygen on the reactant side, 1 oxygen on the product side. I have 1 chloride, 1 chloride. So I'm balanced for mass. But more importantly, I'm also balanced for charge. My total charge on the reactant side is 0. My total charge on the product side is also 0. This plus and minus cancel out. So I'm electrically neutral here and here, so I'm completely balanced for mass and for charge. And I produce H3O plus, so HCl is an acid. It's a little bit more challenging when I do it with bases because of the reactions that occur, but we'll just say sodium hydroxide, aqueous, can disassociate to form sodium plus aqueous plus hydroxide minus aqueous. And again, you see I'm balanced for mass and I'm balanced for charge. Now, because I produced hydroxide, this is a base. Now, what we're going to do in this lab is we're going to measure pH. We're going to measure pH, and that's going to directly measure the H3O plus concentration. The concentration of H3O plus, where the brackets designate a shorthand notation for concentration. Now, if you recall, pH is the power of hydrogen. And that power, again, is a mathematical power. Not again, unfortunately, again, it's not a superpower. So if I have something like 10 to the 2, this guy up here is 10 raised to the 2nd power. So that's the power we're talking about, is this mathematical operation. Now, it's difficult to deal with powers. So we need to get this power down from the exponent. And the way we do that is through logarithms. So to extract that power, what I would do is I would take the log of this. And this would give me 2, which is bringing it down, times the log of 10. So this, when I do this, I'm able to get that power down from the exponent. So that's the power we're talking about, is these logarithmic powers. So to actually use the power of hydrogen, what we're going to do is we're going to take the logarithm of the H3O plus or hydronium concentration. So pH is actually equal to the negative log, there's that power, the negative log of H3O plus concentration. It's also, you can also write it as the pH equals the negative log of the H plus. Remember, that's just a shorthand notation. These are equivalent. Now, why the negative? Why do we have to deal with this negative? That negative is going to cause us some problems how we think about things. But it's important to have that negative in there. The reason is this concentration of H3O plus is going to be less than 1 molar. So we're going to be dealing with concentrations that are 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. And it's that 10 to the minus power that we need to get rid of that minus in the power. So to get rid of a minus, we use another minus. And that's going to give us positive pH values. Now, unfortunately, that's going to flip things around for us. So what we're going to see is something with we're going to have pHs, let's do a scale, a pH of 14, 7, and 1. So here's my pH. But this is going to make things backwards. Because of this minus, this is going to be a basic solution. This is going to be a neutral solution, and the 1 is going to be an acidic solution. So because of that negative, and we have to have that there, otherwise we would get negative pHs. Because of that negative, it flips the way we have to think about things. The lower the number, the more acidic it is. The higher the number, the more basic it is. Okay, so if we know the concentration of H3O+, we can determine the pH. We can also determine the concentration of H3O+ knowing the pH. So how to find our concentration of acid from pH? Well, what we want is we want to extract this from this logarithmic term. We just can't divide by log. Can't divide by log because that's not a number, that's a function. So to get rid of this function, we have to use what's called an inverse function, which in this case is raising things to the power of 10. So the concentration of H3O+ is going to be equal to 10 to the minus pH. So by taking this entire equation and raising all of it to the power of 10, that cancels out the log and allows us to solve directly for the concentration of H3O+. So now, if you're given a pH, you can use this equation to solve for the concentration of H3O+. If you're given the concentration of H3O+, you can use this equation to solve for the pH. What you will be doing in this lab is you will be measuring your pH and finding the concentration of H3O+. Now, interesting thing about water. Water reacts with itself. So when water reacts with itself, we get something that looks like this. H3O+ plus OH minus. So water is both an acid, because we produce H3O+, and a base, because we form OH minus. Now these react together to go back to form water. So this reaction goes backwards and forwards and backwards and forwards, and that's why we use this double-headed arrow. There's a very special constant that's associated with this reaction. This constant, we call it Kw, equals 1 times 10 to the minus 14. And it's a constant, it doesn't change. So when we have this reaction, we also have a pH equal to 7. This is a neutral solution. Now, why this is important is because this constant allows me to take the concentration of H3O+, multiply it by the concentration of OH minus, and that equals that constant, 1 times 10 to the minus 14. So if I know the concentration of H3O+, and that constant is constantly constant, then I can solve for the concentration of OH minus. So again, we can do the algebra very simply. Concentration of OH minus equals 1 times 10 to the minus 14 divided by the concentration of H3O+. And now I can find the concentration of OH minus. So think about what you can do just by measuring pH. If I measure pH, I can use this equation here to determine the concentration of H3O+. Once I determine the concentration of H3O+, I can use this equation to determine the concentration of OH minus. So I can get both the concentration of H3O+ and the concentration of OH minus from one pH measurement because they are related by a constant. And here's the interesting thing that happens physically. When we have two variables related to a constant, they are intertwined. As one goes up, the other has to go down in order to keep that constant constant. So as my solution gets more acidic, the concentration of H3O plus goes up and the concentration of OH minus goes down. Now a more acidic solution is going to have a lower pH. So in a highly acidic solution, I'm going to have a high concentration of H3O plus and a low concentration of OH minus. Now in water, and all the solutions that you will be dealing with in this lab are in water, your concentration of H3O plus and your concentration of OH minus will have to be between, they will be greater than 1 times 10 to the minus 14, but less than 1.0. If you have a concentration that's less than 10 to the minus 14, you made an error in your calculation. So these concentrations have to be between those two. And as you would expect, as the concentration of one goes up, the concentration of the other must go down.